Hello students, welcome back. We just completed section 2. Now let's go to section 3, local behavior. And please be warned, this is going to be hard. Let's begin with a motivating example. Let f of x be a rational function defined like this and determine all intervals in which f of x is greater than 0. In other words, solve this inequality. How do you do that? Well, graph the function, and the function value f of x is a y-coordinate, and we're going to find out the part of the graph where y-coordinate is positive or above the x-axis. Here's a graph. Does it help? To a certain degree, around here above the x-axis, around here below the x-axis, but around here it's really hard to tell. If you know the answer in advance, will it help? That's the solution set, and here's confirmation by Mathematica and the graph. Do they match? They should match, but do you actually see the matching? It's really hard to see. Zooming in may help because you know the answers in advance, so let's zoom those in around the vertical asymptote, around the zeros, and then around another vertical asymptote, and then paste them together. Will those help? They should help, but I don't know whether everybody can handle that. Even I have difficulty understanding all those after a lot of cutting and then reshuffling. In short, we'd like to have better tool. This is not really working out very well. As for the better tool, we are studying it right now. In the end, we'll be able to establish something really nice, but the theory behind it can be a little bit rough, but it is necessary, so let's go through with those. Okay, next, let's take care of some terminologies, zeros and poles. Zero, we already know, the x-coordinate values where the function value is 0. So function value is y-coordinate, so it's the same as hitting the x-axis so that y is equal to 0. So it's represented as the x-intercepts. We already know. The next concept is poles, and that is similar concept for the denominator. And you can call it as the 0 of the denominator and 0 of the numerator, but then again, that's a bit too confusing. We have 0 of a function, 0 of a numerator, and 0 of a denominator. Too many zeros and it's confusing. And also, whenever I use the term 0 of the denominator and emphasize as such, and then of course our textbook author does the same thing, what happened was students just zero in the denominator because the name is 0 of the denominator, and a lot of times they forget about the interaction between numerator and denominator and lose credit. In order to cure all those, I'm introducing a new term, pole. Pole is similar concept for denominators like this. After factorization and simplification, in the lowest terms, you can get zeros alpha 1 through alpha r with multiplicities m1 through mr. That's something we already know. And likewise, you can get poles from the denominator, beta 1 through beta s, with multiplicities n1 through ns. And the poles are represented as vertical asymptotes. You see, pole is a kind of like column, isn't it? That's kind of like a stick that stands, so it kind of looks like vertical asymptotes. Here's an example. We have rather complicated function, but it is possible to factor it, and how to factor this is left to the students. It's a nice exercise. No GCF here, so factor it with respect to x squared, and then factor this blue part further into x plus 2x minus 2, where this black part is left as irreducible. You cannot do anything further. Denominator has GCF of x squared, so x squared out, and what's left is quadratic. Turns out it's another complete square. So we have all this factorization. So what's the conclusion? Numerator gives us x equal to -2 and +2 with multiplicity both 1. Nothing is here That means 1 is hidden. The denominator gives us two poles, x equal to 0 and x equal to negative 2/3, with multiplicities 2 for both of them. Second power, second power. And then here are the graphs. First graph shows the vertical asymptote at the pole, x equal to 0 and x equal to negative 2/3. And then they have even multiplicity. So we're going to end up with the same sign. We have drag, you see. The left-hand side and the right-hand side of the graph drag each other to the same infinity, negative infinity. Same thing goes over here. They do not split, it's a drag. And then as for zeros representing x-intercept cutting through, because we have odd multiplicity, multiplicity 1, that's something we already discussed in polynomials. By the way, these two are the same graphs, just different viewing window. Here, y goes to negative 200. Here, y goes only up to negative 1. So the majority is just cut off here, so that over here and over there are a little bit more visible, as you can see. Now that we went through some examples and also the concepts of zeros and poles, let's now work on the local equivalence and local behavior. Please pay attention here because it's going to be difficult to understand. Okay, here we go. We say a pair of real functions, f and g, are locally equivalent if the ratio between the two is close to 1 around x equal to c. Now, if the ratio is precisely equal to 1, then f of x and g of x are the same. But if they're not precisely equal to 1 but close to 1, then they're going to be kind of similar but not exactly the same. And that's what this local equivalence is all about. Precise definition will require calculus, so we're not going to go there. Instead, let's talk about how to use it. After factorization, we have x minus c to the m power, where m is a multiplicity, and they are the other factors, both in numerator and denominator. Plug in x equal to c to the other factors. If I plug in x equal to c here, then you get c minus c, that's 0, and all 0, I have nothing. So you have to keep this. To the others, plug in x equal to c here and there, and then you get a number times x minus c to the m power. This is basically a power function of degree m, just shifted by c. So it's going to be either u-shaped or upside down u-shaped if m is even, or it's going to be kind of increasing cutting or decreasing cutting if m is odd. We already studied those in polynomial functions. For poles, that's a little bit new, but it's the same idea. Keep this the same and plug in x equal to c to the others. If I plug in x equal to c here, c minus c is 0, and that's in the denominator, so we have nothing. So keep that and plug in x equal to c to the others, like this, and we have a constant, and then times 1 over x minus c to the m power. Now, depending upon the multiplicity, you're going to get the behavior of the power function, drag or split. Drag toward the same infinity, either going up or both going down, dragging each other, or split. One goes to positive infinity and the other goes to negative infinity. That depends upon whether m is even or odd. Let me show you an example here. Around x equals to negative 1, keep this one, and then to everything else, plug in x equals to negative 1, we get this power function shifted a little bit. So it's cubic function. As you can see, locally, we have the same local behavior. In large scale, they do not have any semblance, but locally they do. Here's another example. Around x equals to 2, keep this, and then to everything else, plug in x equals to 2 and do your computation. You have constant, and then this is power function, second degree, so it's going to be parabolic. As you can see, same local behavior. In larger scale, it's kind of difficult to see, but in small scale, you can clearly see this. How about the pole? Okay, go to denominator and then get this one. Keep this. Keep this. To everything else, plug in x equals -1/2. Calculate, we get this constant times this power function. It's a second power function, so it's a drag going to the same direction. Same negative infinity in this case, because negative times this. Final example, around 3/2. So keep this, and to the others, plug in x equals 3/2 and do your computation. You get a constant, positive constant times this power function. So we have split like this. You can clearly see the local behavior. In larger scale, of course, they're different, but locally, they behave the same. So what's the conclusion? We can use the behavior of the power function to get the local behavior of the complicated rational function. How does it help? Finally, the punchline. Finally, the conclusion. Even multiplicity, same sign. Odd multiplicity, sign change. Please prepare this in your formula sheet because definitely you're going to need this for final exam. Here's an example. Hitting 0 and bouncing back. Hitting 0 and bouncing back, either positive or negative. You have no sign change. The same as polynomial function. As for poles, we have drag, either positive or negative. In any case, no sign change. Sign stays as positive around the pole. Sign stays as negative around the pole. So the diagram, no sign change, keeps the same sign. Again, the diagram here. How about this? For odd, we have to have sign change. Around 0, we're going to get hit and cutting through. Hit and cutting through. Either way, we have to have sign change. Minus plus or plus minus. Here's a diagram that's going to be very, very useful because graphs do not reveal too much, or actually it reveals too much information. Now about poles, we have to have split. So here and there we have two different signs. Minus plus or plus minus, either way. Now graphs reveal too much information, so it's often very difficult to see everything. So diagram is going to be very, very useful determining or describing the local behavior around each pole or each 0. Please remember the conclusion. Even multiplicity, same sign. Odd multiplicity, we have sign change. If you multiply by -1 to the odd power, sign change. If you divide by -1 to the odd power, again sign change. If you multiply by -1 to the even power, same sign because that's 1. If you divide by -1 to the even power, again the same because that's 1. Now how do we use all these? Well, here are some example problems which we will do in the next video. And then here are some harder problems that we have to associate not just inequalities but also the local behavior as well, again in separate videos. For now, remember this.